All right, so this is my final project for GIS 512, and I'm Andrew Hillman, and my project is Miscanthus spatial variability. So Miscanthus is a tall grass that is mainly grown for bioenergy purposes, and in my research is interested in the environmental impacts of growing Miscanthus in North Carolina. So my research question as it pertains to this project is, can we quantify different types of spatial variability from UAV imagery? Spatial variability could be in terms of water stress, evapotranspiration, plant biomass, leaf area, anything like that. So the data I'll be using for this project is from a UAV flight that was flown on November 11th this year, so fairly recent. It was done by the staff in the Bio and Ag Engineering Department with a green-blue near-infrared sensor with a resolution of 2.4 centimeters per pixel. And this orthomosaic photo on the right is the raw output after it was stitched together. So the methods I used for this project were the vegetative indice known as ENDVI, which stands for Enhanced Normalized Differencing Vegetative Index. And I had to use the raster calculator to use this formula because ArcGIS Pro does not come packaged with ENDVI, just regular NDVI. You can see it uses near infrared, green, and blue, which are the three bands I have in my data. So I also traced feature classes, both polygons and lines, created buffers, and ran the zonal statistics tool. So here's a quick flow chart of the image processing project. So first, the images were stitched together in PrecisionHawk software and then exported to ArcGIS Pro as a TIFF file. I used the raster calculator, like I said before, with the ENDVI formula to come up with the ENDVI output file. I then added feature classes to the map and traced each individual row in the field. There's 7 of them. I used the zonal statistics to get the average ENDVI value for each of those rows, and then added another feature class in order to trace the row edges, created a 1 meter buffer to the inside of the rows, and then used the zonal statistics tool again to get the average ENDVI value for each 1 meter row edge. Then this could theoretically be repeated for any other zones of interest in the field that you're interested in analyzing for variability, as well as with any other indices that you're able to calculate. Then manually insert the files into Excel if you want to do further analysis and statistics, and export the output raster files for more permanent files. So here's some images for results. Here's the composite orthophoto on the left that I've already shown. And on the right is the output from the raster calculator with the ENDVI formula. On a scale of red being the least healthy, and the most negative, and green being the most positive, the most healthy plants, a scale of -1 to 1. So as you can see on the left, this is the output from the 7 polygons that I drew around each row in the field. And in the table, you can see the average ENDVI values in each of those polygons, and I've visualized it with a color ramp symbology. On the right, similar symbology to label each of the 1 meter row edge polygons. You can see that ENDVI in those polygons is actually slightly higher than the ENDVI average for those same rows, which is surprising. So in conclusion, we were able to measure variability throughout the field in terms of the rows and the field edges. And the purpose of this is to determine where we want to instrument and sample in the field for future studies. And again, this will be great to extend to other zones of interest throughout the field. With other vegetative indexes, you can look for different forms of variability. In the future, we prefer to use the true NDVI value as it's more widely used in the industry and in research. However, we don't have the red band, so that wasn't possible for this project. And for some temporal information, we'd like to run the same process on images of the same field at different growth stages throughout the year to get some better information about what's happening. Thank you very much.